Hello everyone, today we're going to talk about Gaussian mixture models. The goal is to explain how to use Gaussian mixture models to perform clustering. The prerequisites are Gaussian random vectors and joint distributions of discrete and continuous random variables. We're going to talk briefly about Gaussian random variables and Gaussian random vectors at the beginning to try to make this as self-contained as possible. Alright, so a Gaussian distribution is a bell-shaped distribution that has a mean parameter mu and a standard deviation sigma. It has this is the function that gives you the density. The mean tells you where the density is centered. The standard deviation tells you how spread out the density is. Okay, so here the mean is 3, the standard deviation is 1. Here the mean is -2, standard deviation is 2, so more spread out. Here the mean is 0, standard deviation is 4. Okay, so how do we fit the parameters of a Gaussian distribution? What we do is we maximize the likelihood, or equivalently, we maximize the log likelihood. Okay, so here you see two arbitrary Gaussian lines. They don't fit the data very well. The data here, this histogram tells you, this is a histogram of heights, I should have said this. It tells you the fraction of people that have certain heights. We would like a Gaussian that adapts to the heights, and for that we have to choose the appropriate mean parameter and standard deviation parameter. So how are we going to do that? We do this by maximizing the log likelihood, which basically maximizes the density of the Gaussian model at the observed data. Okay, so this is the log likelihood function, and I encourage you to review this if you don't remember this very well. And when we write it out, so this is the Gaussian distribution, it's important to maybe point out that here we're making the assumption that each data point is distributed according to the same Gaussian distribution and that they're all independent. So then their joint density becomes the product of their marginal densities. And when we take the logarithm here, okay, this is the logarithm of the joint density becomes the sum of the logarithms of the individual densities. And we plug in the Gaussian model with respect to, also actually, this should be xi. So good that I looked at this a little bit more carefully. Probably you hadn't realized that there's a stray a here. And what's funny is that I just did the video on Gaussian discriminant analysis and I didn't notice. So this will be our little secret. But anyways, the point is that you write the product of the densities, you take the log, you get the sum of the logarithms of the densities, you interpret that as a function of the parameters because you want to tweak the parameters so that the density is as high as possible at the observed data. That's maximum likelihood. And what this tells you is that you should choose the mean parameter to be the sample mean in your data. That makes a lot of sense. And you should choose your standard deviation parameter to essentially, or here I'm writing it as the variance. You should choose your standard deviation parameter so that the variance corresponds to the sample variance. Okay, sometimes the sample variance has an n-1 there, but it's almost the same as the sample variance. Okay, and again, this was a small mistake. Sorry about that. I went very quickly through this because this is just a little bit of context. How do we fit Gaussian distributions? We use maximum likelihood, and what that amounts to is the mean parameter becomes the sample mean, the standard deviation parameter becomes the sample standard deviation. And that gives us a very good fit, in this case, on this height data. Gaussian random vectors are generalizations in multiple dimensions of Gaussian random variables, where instead of just a mean and a standard deviation, you have a mean vector and a covariance matrix. Let's go to the contour line, well, to the density. Okay, so what does the mean vector tells us? It tells us where this density is centered, and the covariance matrix tells us how it's spread in different directions of space. Okay, so these are the contour lines of this same density, and the contour lines look ellipsoidal, and I don't want to get into a lot of detail, but basically the axes of this ellipsoid are given by the eigenvectors of the covariance matrix parameter, and how spread out the density is in the direction of those axes is given by the corresponding eigenvalue. Okay, so basically the covariance matrix tells you how spread out the Gaussian random vector is, the density of the Gaussian random vector is in different directions of space. Again, I'm going very quickly through this because this is just review. how do we estimate the parameters of a Gaussian random vector? You write out the log likelihood and you realize that it's maximized by setting the mean parameter to the sample mean. Makes a lot of sense. In this case, this is a sample mean in d dimensions, so realize that. And the covariance matrix is just set equal to the sample covariance matrix. Very similar to the 1D case. Quick example, you have height and weight here. So we're in 2D. And this is what the contour lines of a non-parametric kernel density estimate is, of the density. And this is what the Gaussian model looks like. Okay, so pretty good. And again, what have we done? We have averaged all of this to find the center. And then we have computed the sample covariance matrix to figure out, how spread out the density is with respect to the center. Okay, so now let's introduce Gaussian mixture models. I've already introduced them in the video of Gaussian discriminant analysis, but let's go through the reasoning again just very quickly. We have a data set which has men and women in the United States Army. If we fit a Gaussian directly to the whole data set, it's not great. Okay, we see that the fit is not very good, so we want a better model. And what we do is we realize that if we just fit the men using a Gaussian, we actually get a pretty good fit. And we'll see that with the women it's the same. So we build a model that mixes these two Gaussian. That's why it's called a Gaussian mixture model, based on a discrete random variable, which is sex. Okay, so the conditional distribution of height given sex is going to be Gaussian. And the distribution of sex is just the fraction of men and women. Okay, that's really easy. So we are able to estimate the parameters of this joint distribution from the data. And then we can put it all together. Oh, sorry, let me show you first the conditional distribution of height conditioned on female, okay, and conditioned on male. Okay, so pretty good. It's a pretty good fit. Now, what if I want the marginal distribution of the whole height? We did this again in the video on Gaussian discriminant analysis. The idea is very simple. You just take a sum of the two conditionals weighted by the corresponding probabilities. Okay, the probability of male times the conditional given male plus the probability of female times the conditional given female. These are these conditional Gaussians. So you sum them together and you get this very nice Gaussian mixture model that actually fits the data very, very well. Okay, we're very happy. Much better than the Gaussian model, so very happy. But now, okay, what if we don't know the labels? So remember, in Gaussian discriminant analysis, we do classification based on a Gaussian mixture model, where in the training set, we happen to know the labels that determine the different conditions. But what if someone gives you this height data and doesn't tell you that it consists of men and women? You actually just don't know. You just have the height data. What can you do then? Okay, if you fit a Gaussian, it's not going to be great. So can you actually fit a Gaussian mixture model without knowing the discrete labels? And it turns out that you can, and we're going to see how. Okay, so the first thing we have to do is we have to assume that these latent variables exist. Here we're going to assume that we know that, or we know that we impose at the beginning that we're going to fit a mixture of m Gaussians. In practice, you would actually want to choose m wisely, and typically what you would do is you might have some held out data and see how the different models do. Of course, the more Gaussians you're going to fit, the better you're going to do on your training data, but it might not generalize as well, or it might not produce as big a benefit, and you might say, okay, I just want to interpret this data in terms of m clusters. We'll introduce clusters a bit later on, but the idea is that if you in this case, in the height data, for example, if we fit a mixture model with two Gaussians, then we can assign a cluster of data to each Gaussian and separate the data like that. Okay, I've gotten a bit ahead of myself, but that's why I just said clustering. Anyways, okay, so if we want to fit a Gaussian mixture model and we don't have access to these discrete random variables, what we're going to do, we're going to introduce them into the model and jointly estimate them together with the other parameters of the model. That's what we're going to do. Okay, so we're going to assume that we have a mixture of m Gaussians, where x represents the data, and we have an additional latent or hidden or unobserved random variable k, which we don't see, but we're going to assume so that we can build the Gaussian mixture model, and we're going to learn its distribution together with the Gaussian mixture model. So the idea is that the conditional distribution of x, given that k has a certain value, is going to be Gaussian, okay, with certain parameters mu, mu k, and sigma k. And this is what we're going to fit to the data. Again, without having observed k. That's the key difference with Gaussian discriminant analysis. The challenge is, how do we fit the model if we don't observe k? If we observe k, where like in Gaussian discriminant analysis, life was really nice, right? Because what do you do for mu? You just average the points with that particular class. What do you do for the covariance matrix? You just build a sample covariance matrix using those points. Boom, you're done. Okay? Now things are going to be a little bit more complicated. We're going to assume that the number of clusters m is known, or the number of classes, whatever you want to call them. Again, in practice, you would have to choose this wisely. Probably you would try with different values of m, and you would decide based, for example, on held out data. So we need to find, first of all, the PMF of k, okay, the fraction of data that we think belong to each class. In the case of men and women, how many men do we think there are, how many women there are. Of course, we wouldn't call them men and women, right? Class 1 and class 2, how many people in class 1 we think there are, how many people in class 2. We also need the mean of the data in each of the classes. Okay, that's called mu k, and the covariance matrix, because that parameterizes the Gaussian distribution corresponding to each class. And actually, that's it. Okay, I was saying this as if there's more. That's it. Okay, this is what we need to fit the model. But we're also going to, I got a little bit ahead of myself. What I was going to say is that we are also going to compute some membership probabilities. But first, let me tell you, I'll get to the membership probabilities in a moment. Let me tell you first about the conditional likelihood. We're assuming IID samples. Okay, so if we knew the class K of each of the samples, if we knew this person is man, this person is woman, or whatever other class we could have assigned them, in that case, the likelihood is just Gaussian, right, with the corresponding covariance matrix and the corresponding mean vector. Okay, so in that case, things are easy. But now we don't have it, right? So we need a likelihood that just depends on the actual data, not on these labels that we don't observe. So what do we need to do? Remember, in the mixture model, what we do is we have if we want the marginal of the continuous random variable, so in this case x is the continuous random variable, which is what we observe, or the continuous random vector rather. Okay, we are observing x1 to xn, so we're observing x1 to xn that are samples from this random vector. Here we're assuming IIV. Okay, so this is actually fx 1 to xn. So we're looking at the joint distribution of the different data points that we're seeing, and we're going to assume that this joint distribution is just equal to the product of the marginals. Okay, this is what we often do in likelihood estimation, because they're independent samples, but they have the same distribution, right? So what does that distribution look like? It's a mixture model that depends on k. So how do we find the marginal of the continuous random variable? We sum over the possible classes, we multiply by the probability of each class, and then we multiply by the conditional density. This is what, like, we were exactly the same as before, when we were taking the conditional Gaussians, multiplying them by the corresponding probability, and summing them together to build the mixture model of the height data. Okay. The only difference here is that we don't know k, So, but that's okay because we are summing over it here. As we will see, it's okay. This is a little bit up for debate because now we have this function here. This is the likelihood that we would want to maximize with respect to these parameters. But the problem is that when we take the logarithm of this to try to do the maximization, typically you take logarithms because this is going to have super small values because you're multiplying probabilities over and over and over. Imagine that you have 100 data points or something. So typically you take logarithms so that this value is not ridiculously small. It doesn't change anything because it's monotone. When we take the logarithm, we realize that we have a very weird looking function. We have a sum of a logarithm and then a sum inside. It turns out that this function is very difficult to optimize. It's very difficult to maximize with respect to these parameters. You can try to do it with gradient descent, and there's many methods to do it. We're going to talk about the most popular of them all, but they're all heuristics that get you to a local maximum. That's all you can get. Luckily, that local maximum is often very useful for data analysis. But we're a little bit out of our usual. So you have seen other videos that I've posted when we were looking at how to estimate the parameters of a Gaussian, the parameters of an exponential, of a geometric. Life was really easy because we built the likelihood, then we built the log likelihood. It was concave, it had a single maximum, closed form solution with respect to the data. Typically, you just average the data points or something to find the parameter. Great. Here, that's not the case at all. Okay, you have a log likelihood that is very weird. It has a lot of local maxima. The only thing you can do is try to reach a local maximum, and hopefully that will be useful. Okay, and it's important to bear that in mind. In order to do this, okay, and this is what I wanted to say before I got ahead of myself, we're going to define some membership probabilities. We'll see in a moment how they are helpful to maximize the log likelihood, but first let's actually define them. These membership probabilities tell us the probability that data point I belongs to class K conditioned on the actual features. Okay, so in the case of height, this would be the probability that this person is in class 1 or class 2 based on their height. Okay, this is super useful for clustering, which is basically classifying the data points into these different classes that we're defining, because this is what we're going to use, right? If the probability of them belonging to class 1 is higher, we'll assign them to class 1. Okay, that's the idea. How do we compute this probability? It's exactly the same as when we talked about Gaussian discriminant analysis in the other video, and we wanted to find the probability of the discrete random variable given the continuous random variable. We apply the chain rule for continuous and discrete random variables. This down here is just equal to f of xi xi according to the mixture model. Okay, so because this guy times this guy is equal to this by the chain rule. That's the idea. We can plug in, so if we knew all of the parameters of the model, this is easy to compute. We just plug in, remember that this is this Gaussian likelihood. I just didn't want to write out all the Gaussians all the time. For class K, down here you basically compute the whole mixture model, because that's, again, this is the probability of, the density of fxi. Okay, so if we know the parameters, it's easy to compute these membership probabilities. This is the same thing that we're doing when we're doing Gaussian discriminant analysis. Okay, but of course the whole problem is that we don't know these parameters. We need to estimate these parameters from the data. A quantity that would be interesting is if you sum all of these probabilities for class K over the data, because this kind of tells you the effective number of points, of data points in that cluster. Ideally, these probabilities, by the way, would just be 1 for the true class and 0 for the rest. If that were the case, then this would just give you the number of points in that class. Of course, it's not going to be the case. So it's kind of an approximation to how many points there are in that class, more or less. So when we do clustering, as I was saying before, if you have the membership probabilities, then what are you going to do? You're going to say, oh, for this point xi, what is the class that has the highest probability? I'm going to assign it to that class.
Okay, so that's a way of doing clustering based on the Gaussian mixture model. Of course, again, in order to have these membership probabilities, you have to estimate the parameters of the mixture model, and that's the key challenge. How do you estimate them? What we're going to do here is we're going to describe expectation maximization, which is a little bit of a weird name. In order to properly justify it, you have to connect it to a more general algorithm to fit Bayesian models. We're not going to go down that route because it gets very complicated. What we're going to do here is we're going to provide a very intuitive description of the algorithm and explain why it makes sense. And I recommend that you go to more advanced books on machine learning and Bayesian estimation to read more about expectation maximization. Okay, so here I'm just going to provide some intuition. The idea is that we're going to jointly estimate the parameters and the membership probabilities, because if we assume that we know the membership probabilities, it turns out that we can get a very reasonable update of the parameters, a very reasonable estimate of the parameters, I mean. Okay, and if we know the parameters, we definitely know the membership probabilities. So what we're going to do is we're going to initialize the model parameters in some way, and then update them, first estimate the membership probabilities, update the parameters using those membership probabilities, and then alternate. This is a heuristic, but as we will see, the heuristic makes a lot of sense, and you can actually prove that in each update, you're always increasing, or at least the log likelihood does not decrease. So at least there's that. That's actually a little bit complicated to prove, so we are not going to prove it here. But you can actually prove that. Anyways, let's get to it. First, we're going to see what the update is for the membership probabilities, assuming fixed model parameters. And then we're going to look at the update for the model parameters, assuming fixed membership probabilities. So the first update, we already did it, right? If we know the model parameters, computing the membership probabilities is just applying the chain rule. It's equal to this. So we're done. And with that, we can also apply, we can also compute the effective points in each of the classes, which is going to be useful for the other update. The second update is a little bit more complicated. Okay, and here is where we're mainly going to give intuition. In order to derive this, what you would actually do is write out the log likelihood and see that if you fix the membership probabilities and you maximize with respect to the other parameters, you get these updates. That still doesn't mean that you have maximized the log likelihood, right? Because the membership probabilities depend on the parameters, so it's still a heuristic. But anyways, now I'm just going to give some intuition. So alpha k is the probability that of any data point belonging to a cluster K. So if we knew the assignments to the classes, what would we do? We would just set alpha k equal to the fraction of points in class K. We don't have that. But if we know the parameters, if we know the membership probabilities, we have the effective number of points in each parameter, in each class. Okay, I feel I'm breaking down here. Okay, I think let me get myself together, pull myself together. We have the effective number of points which we obtain by just adding all the membership probabilities. That's kind of like a proxy for the number of points that end up in class K. So we can actually compute that divided by n. This is going to give us a very reasonable estimate of the probability that you belong to cluster K, as long as the membership probabilities are well estimated. Okay. Let's see how we would update the mean parameter for class K. So remember, if we knew which points are in class 1, which points are in class 2, like we did for the male and female, for the men and women, what would we do? We would take all the men and just average them. Okay, so we take the data in cluster K and we would just average them. That gives us our mean parameter. We don't. But what we can do is we can weight each point by the corresponding membership probability as if it was kind of a soft assignment. Like if the membership probability is 0.9, we think that probably the point belongs there. If it's 0.1, then probably not. So if you multiply the points by that soft assignment, by that weight, you're kind of doing a mean that is weighted by your beliefs about whether the points belong to that class or not. So if the only thing you have are the membership probabilities, a very reasonable way of estimating the mean of that cluster. If the membership probabilities were perfect and they told you they were 1 for the elements of that, for the data points that are actually in that class, then this would be great, this would be perfect. So we're relying on the membership probabilities being precise. We can do the same thing for the covariance matrix. If we knew the points that were in class K, what would we do? We would just compute the sample covariance matrix, which is this average of this outer product for each point where we have subtracted the mean. That's what we would do, right? We would average it only over the points that belong to the class. We don't have that, but what we can do is we can weight this average using the membership probabilities as soft assignments, and this gives us a reasonable approximation if the membership probabilities are good. Okay, so we have derived the updates of a model in an intuitive way, assuming that you know the membership probabilities. So the idea is that you somehow initialize, for example, you can do like k-means or something to kind of separate the points. You can compute the model parameters with this initial crude clustering. People often use k-means to initialize these things. And then once you have those model parameters, you compute the membership probabilities and you improve the model parameters using those membership probabilities, and then you alternate, right, between update 1, update 2, update 1, update 2. So what happens if we apply this to our example with the height data, where we're going to assume that we don't know about men and women, we only have the heights. Here I'm showing you how the iterations go up, and eventually it seems to converge to some local maximum of the log likelihood. Okay, these are the values of the log likelihood. Again, if we just looked at the likelihood, they would be extremely small. That's why we take the log. It's increasing, so that's a good sanity check if you're implementing this. Increasing, and eventually it plateaus. Let's take a look at the estimates for the fraction of points in each of the classes. We see that they end up around a little bit more than 70%. It's interesting to compare this to the true. So in this very special case, we actually know that men and women are a reasonable way of clustering this data. And what we see is that the fraction of men is 67%. Okay, and here we converge to a little bit more than 70%. So it's actually pretty close. And again, the algorithm knows nothing about men and women. We can look at the parameter, the mean parameter. The mean of class 1 is here, around 74, I want to say. Here, this one is 161, more or less. And now we can see the mean of the men and the mean of the women, just as a sanity check. There's no reason why you would need to necessarily converge to exactly that, right? And there's also other factors that determine height beyond sex. So we shouldn't take the Gaussian, the two Gaussian models as like the ground truth, but it's pretty close, right? So here, the average height of men is 176, the average height of women is 163. So the model is actually picking up that men and women is one of the most important factors to cluster this data. Same for the standard deviation. We end up with a standard deviation for men that is around 7 and for women that is around 6. And that's actually quite close to the actual standard deviations. This is what, when we start the iterations, this is what the clustering looks like. It's pretty terrible. Here I just initialized it in a bit of an arbitrary way. I think by just, like taking the mean of the population and just plus minus something. I think that's how I initialized it. So this is, iteration 1, pretty bad model parameters. These are the membership probabilities. So, not great, but still, it picks up the fact that, the probability of one cluster, the probability that, of a certain class for higher height is higher, and the probability of the other class is higher here. And that actually helps, because when you start iterating back and forth between the membership probabilities and the parameters, you start obtaining this iteration 100. So, super fast, but still, it starts kind of separating the two Gaussians to fit the the data better. And this is how the membership probabilities look. So they're looking much more reasonable. And eventually, you converge to a pretty good fit. And again, the underlying Gaussians that you find are actually incredibly quite close. Well, incredibly. I mean, I was actually quite surprised to what extent this finds the men and the women automatically. So it does find that clustering based mostly on sex automatically. And you get a pretty good fit to your data without having had to have access to the labels originally. This is often called unsupervised analysis or unsupervised learning because we don't have supervised labels when we're fitting them all. Okay, and this is finally what we get in terms of the membership probabilities. Okay, so this is the probability of male for high heights is almost 1, almost 0 here. Probability of female is very high for small heights. But again, the method knew nothing about male or female when we were fitting them all. Now I'm going to show you another example where we have, just to show you what happens with Gaussian random vectors as opposed to just Gaussian random variables. It was easier to work with Gaussian random variables when we were explaining, motivating and explaining the model, but often you apply this to data that has more than a single feature, more than just height in that case. So here I'm going to show you data, I'm showing you data with 2 features. These are rebounds per game and assists per game for NBA players between 1996 and 2019. So a point here would indicate that this player had about 7 assists per game and like 11 rebounds. So this is a player that rebounded a lot and passed very well. Maybe Nikola Jokic or someone like that. Actually, Jokic would probably have even more assists. And now what we want to do is automatically cluster players according to these 2 features, according to rebounds and assists. These lines here are contour lines of a density, of a kernel density estimate. Okay, so just by looking at this, not immediately obvious how to cluster the players. So what we're going to do is we're going to fit a Gaussian mixture model with 3 Gaussians and see what happens. And this is what happens. We obtain these 3 conditionals. For one, the mean is here. For the other, the mean is here. For the other, the mean is here. Okay? And actually, this clustering makes a lot of sense because what are we getting? We're getting players that had more assists, players that had more rebounds, and then players that didn't have many assists or many rebounds. And this is, I don't know how interested you'll be in basketball, but if you're interested in basketball, this makes a lot of sense because oftentimes shorter players are guards or small forwards. They tend to grab less rebounds unless they're like Russell Westbrook, but I don't want to get controversial here. Whereas tall players tend to grab a lot of rebounds but don't pass very well, with exceptions such as Jokic, for example. Okay, so this is actually something that, if you know about basketball, is actually very, very reasonable. It's always important to sanity check the results of your data analysis. So what we can do here is actually we can look at the heights of the players in each of these 2 clusters and see whether indeed we would expect these guys to be much taller than these guys if we have actually separated players according to their role. Again, this is just a sanity check. And when we look at the heights, that's exactly the case. Okay, so we have that these players in cluster 2, this cluster 2, are much taller than the players in cluster 3, which indicates that automatically, just looking at the assists and rebounds, we have been able to separate the players that are, like taller, play closer to the basket, with the players that are more that distribute passes and play as guards. Okay, and we confirm this with this sanity check where we see that the shorter players are the ones that are assigned to the cluster that gives more assists. And I'm not showing this explicitly, but the way we fit this model is exactly by expectation maximization. Okay, where we alternate between updating the membership probabilities and updating the parameters of these 3 2D Gaussians. This is a good example. We're choosing 3 clusters. There might be more clusters. Depending on what you do with your analysis, you could actually just try with different numbers of clusters, see how they fit the data, see if something else pops up. You know, for all we know, we could have like an additional cluster that has a small number of players that might also be interesting. You know, especially if you have more features, that would probably be the case. All right, so what have we learned? We have learned how to fit Gaussian mixture models using unlabeled data, applying the expectation maximization algorithm, and we have applied it to an example where we clustered NBA players. Thank you very much.